Today's lecture, and probably next week, is about compactness. I would say that up until now, basically, this course has been fairly shallow. So, and that's not to say it's easy, but we've made a lot of definitions and sort of scratched the surface of a bunch of things, and there's been some linear algebra that we've used to analyze situations in geometry. But now we're actually getting into something deep. So compactness is really a deep idea. In this course, we'll unpack like the first two layers of it. One is the approach in the setting of metric spaces, where it will have a kind of intuitive content, which is familiar to you from real analysis. Say, I hope you've all seen the proof of Bolzano-Weierstrass, but we'll go through it again if you haven't anyway. So, I mean, compactness kind of makes sense. Intuitively, it's some property that is possessed by an interval, but not by the whole real line. So there's a sense in which this is finite and this is not, and that's the notion that's captured by compactness. But really then we'll discover that this notion, which we'll formulate in terms of convergent subsequences, is not really a metric property, so it's actually a property of the topology, although characterizing it in the topology does lead away from our intuition a bit. So that will feel more strange, that characterization, but it's genuinely a deeper characterization. So then we're going to use that notion of compactness in topological spaces to prove some deep theorems about compactness. And I'd say this is the first time we're really touching some genuinely serious mathematics when we're discussing compactness. Okay, so what's the point? Why are we caring about this particular property of intervals? Well, you know at least three special things about intervals. This is one, the extreme value theorem, right? So this is employed over and over again if you're trying to put the foundations under calculus of one variable, right? So a continuous function on an interval is bounded, that is, it has the set of values it takes is a bounded subset of R, and moreover it attains its extrema, right? In the precise sense I've indicated there. So another important fact that you should have seen about the unit interval is that a continuous function on the unit interval is uniformly continuous. I'll talk about that in a future lecture. I don't want to spell that out now. That's another important property of continuous functions on an interval, which is not true of continuous functions in general. And another important property of a continuous function on an interval is that the Riemann sum exists, right? Riemann integrals work for functions on an interval. So there's some property that the interval possesses which sort of explains all three of those things, and that is compactness. And I mean that previous couple of sentences in the following precise sense. So we'll take compactness, we'll formulate it for arbitrary metric spaces first of all, and all three of these things, this not quite so much, but at least the first two things will then work for any compact metric space. And the notion of compactness or functions which have compact support will be the basic point we're going to start from to, first of all, talk about Riemann integrals over compact subsets of Rn, and then from that we're going to get to Lebesgue integrals without having to go through measure theory, so that will be a little bit of a trick. So we'll do Lebesgue integrals, and that's going to be what the whole part of the course about Hilbert spaces is revolving around Lebesgue integrals. But that's built on Riemann integrals, which is built on compactness. Okay, so you've got some idea of how important this concept is. All right, so that's the introduction. So I want to start off just in R. Right, so we're going to go through the proof of Bolzano-Weierstrass because the ideas there are basically the core ideas even in the general setting, so it's worth reminding you even if you've seen it. So remember that a subset of R is bounded if it fits in one of these intervals. Of course, it doesn't matter if I take an open or closed interval. right? So that's just whichever. Put an open interval there if you like. Okay, so given a subset of R, the point is an adherent point. Of X if either of the following two equivalent conditions are satisfied. So it's an exercise to check that these conditions are equivalent. The first says there is a sequence AN in the subset which converges to X, and the second says that what? So for all epsilon greater than 0, there exists a y in X such that the distance is less than epsilon. Okay, X is called closed if it contains all its adherent points. Well, we've defined the term closed already in the setting of topological spaces, and therefore in R is a metric space, therefore a topological space, so the notion of a subset being closed has already been defined. But this is the notion of closed you've seen in real analysis, so, and the two definitions are consistent, needless to say. So let's check that. Now, I hope you notice that both of these conditions sort of have natural generalizations to any metric space, right? So that will happen in a minute. But before we do that, let's just check. That this definition in terms of limits and convergence matches with the definition, which is that the complement of X contains an open ball around all of its points, right? That was the notion of being open in the topology on R coming from the metric. All right, so let's do that direction. So let's suppose that it's closed in this sense, so it contains all its adherent points. We need to show it's closed in the topology. So we need to show, in other words, that the complement is open. That's the definition of being closed. So I'm going to argue by contradiction. So suppose it's not. Well, then there is an X not in X. All right, so here's, it's a bit odd to draw R as a circle, I suppose. So there's R, there's my subset X. If the complement was not open, then there would be no open ball around X which was contained in the complement, right? So that means for all epsilon greater than 0, we have that this open ball is not contained in the complement. That is, that this ball intersects X somewhere, right? That's what that says. Okay, but you see what this is saying, right? It's saying no matter how small I make the distance, I can find some point in X which is also within that distance of little x, right? But that's precisely the second condition there, if you like, right? there is a y in x with x minus y less than epsilon. Okay, but that means that x is an adherent point of little x is an adherent point of x which is not contained in x. But it's not in x by construction, so we have a contradiction. Okay. That's a contradiction to the hypothesis that the complement was not open. Okay, so therefore it's open. The reverse direction. Okay, so suppose it's closed in the topology. We need to show it's closed in this sense. Maybe I'll just sort of say it out loud. So, okay, so if it's closed in the topology, that means the complement is open. Suppose we had an adherent point of x. Well, it's an adherent point of x. If it was not in x, then I'd be able to find some ball around it, which is contained in the complement. That's the definition of being open. But that would contradict the second point there, right? Because then I'd have a ball which is not containing any point of x. Okay, so the details are in the notes, but the idea is essentially similar. So maybe I won't go over it. Okay, so that's the consistency of the limit notion of closed with the definition we've had already. Okay, so I've defined closed and bounded, and any interval in R is closed and bounded. Example, yes. I mean, the boundedness is clear, I guess, for closedness. I mean, you should have checked this when you did real analysis. So. Okay, so if we're trying to abstract some property of intervals which is responsible for these useful facts, what we want to do is find a characterization of this property of being both closed and bounded, and it's the following. So if and only if every sequence in K contains subsequence converging to a point in K. All right. So it's not the same to say it contains a convergent subsequence, right? It contains a subsequence which converges not to just a point, some point, but to a point in K. Right, I think it's clear what a subsequence is. So given a sequence, if I have indices n1 less than n2 less than n3, then a n I, well, let's say n0. Okay, so a subsequence is an increasing sequence of natural numbers, and then I take the subset indexed by those. Okay, who's seen the proof of this? Complex analysis. Okay, good. So I'll be somewhat brief then. Okay, so let's do, well, Since we've all seen it, maybe I'll choose the direction which is informative for us rather than go through it all again. Okay, so there's two directions, right? So suppose it's closed and bounded, then prove that it contains, that it has that property, and then there's the reverse. Okay, so let's do the converse. So suppose K has the stated property. Then, okay, so K is closed. And this is the more important part for us because staring at this argument, you'll see that it generalizes to a metric space, basically verbatim, all right? So that's why I wanted to remind you of it. So what are we going to do? We're going to show that K is closed. So let's suppose, well, okay, so suppose not. So suppose X is not in K, but X is an adherent point of K. Right, so for each n greater than or equal to 1, take my epsilon to be 2 to the minus n. Then the fact that x is an adherent point of k says that there exists some y, and we call that yn, I guess, which is both in k, x is now k, which is in the ball of distance 2 to the minus n of x. Right? Okay, so the sequence yn well, it converges to x by construction, right? But the hypothesis says that it contains a subsequence converging to a point in K. So let me write YNI for the subsequence, right, with the notation that I just described. And that converges to some y in K. Well, but I mean, if a sequence converges to some real number, then any subsequence also converges to that real number. So by uniqueness, I mean, a sequence can't converge to two real numbers, right? So the whole sequence converges to x, so any subsequence converges to x. So I have this sequence, the subsequence, converging both to x and also to some point y in k. And since limits are unique, right, you can't have one sequence converging to two different numbers. We have that x is equal to y, and therefore x is in k. But that's a contradiction. Okay, so this contradiction implies that x must have, I suppose that implies k is closed. All right, so you see here the concepts we need to generalize to metric spaces to make this proof work. We need to figure out, we need to define convergent sequences, that's okay. We need to prove that with that notion of convergence that a sequence has a unique limit, and then this will just work. All right, any questions about that part?
Just that it doesn't really have to be by contradiction. It's discussing.
Oh, that's true. Yeah.
It's not.
Yeah, that's a relevant point. Yeah. Yeah, so actually, Arun Ram, who usually teaches this course, has a bit of a crusade against proofs by contradiction. So, yeah, some slightly odd form of constructivism, I would say, but there's some, I mean, don't get me wrong, there's value to avoiding proofs by contradiction if you can. There's genuine value to that. I think it contorts, I mean, a lot of these proofs, this one is not an example, but a lot of these proofs do work a lot more efficiently if you use contradiction, so I'm going to do it. But there is genuine value to avoiding it, even though it tends to make the proofs a bit more verbose. But if you're interested in seeing that kind of argument, you can look at his notes for this course. I recommend that. Yeah. Okay, so let's prove K is bounded. Okay, again, proof by contradiction. Okay, so what does it mean to say it's not bounded? Well, it means that for all m's, let's say greater than or equal to 1, that K is not contained in this interval, right? So choose for every n some xn which is in K but is not in this interval. Right? So that's some point that's sort of marching off to infinity, right? But within K. Well, by hypothesis, that has a convergent subsequence. Say xnk, xni. But that can't work, right? Because say the xni's converge to whatever, some number x. Well, that x lies within, one of those intervals for some integer, right? And then for for n sufficiently large, we have to have that xni lies inside there as well. Well, choose x to actually be in the open interval, I suppose, right? We can do that by increasing m by 1 if you need to. Right, since xni converges to x, I can make it lie within that interval, but that contradicts the whole setup with this containment, right, for the sequence. Because I chose the xn's to not be in there. Okay, so that contradiction shows you that K must be bounded. All right, so that's the argument for the relationship between this condition on sequences and closedness and boundedness. So now what I want to do is take the ingredients here, generalize them to metric spaces. We'll have a discussion about sequences and convergence and so on in metric spaces, and then we'll come back after that discussion to formulate the appropriate notion which generalizes this business with sequences having convergent subsequences, but in a metric space. Okay, so take a metric space. We say a sequence xn converges to x in x if, so it's the usual definition just with open balls, so if for all epsilon greater than or equal to 0 there exists an integer n I hope it's, I could just write this, but then I'll have to flag that I have to decide whether 0 is in n or not. And I want my n to contain 0, so I don't want to write this. Okay, anyway, so n is an integer, all right? That's clear from the way I'm going to use it. So for all epsilon greater than 0, there exists an n greater than 0 such that n greater than or equal to n implies that xn belongs to that open ball. Right, so I don't think I'm going to motivate that because you've all seen convergence in R and it's just the same definition. Right? Okay, so in this case, we write that the limit as n goes to infinity of xn equals x. Right, as usual, there's no requirement that any sequence, a sequence can converge or not. But if it has a limit, it's unique. All right, so this hinges on, I forget which axiom of metric spaces it was in my enumeration, but the fact that if 2 points are distinct, their distance is positive. Right? Okay, so suppose that we have, so another piece of notation is we usually write this kind of thing, right, to indicate the sequence converges to x. So suppose that the sequence xn converges to 2 points, x and y. I didn't say distinct points. I'm not going to argue by contradiction again. Let's just suppose that we have 2 points, possibly the same, hopefully the same, and to which the sequence converges to both. All right. Well, let epsilon be the distance. We want to show that's 0. Right? If we can show it's 0, then x must equal y by the axioms of a metric space. Well, we know that this sequence converges to x. So we can find an integer such that for n greater than or equal to capital N, so we use epsilon on 2 for our epsilon in the formula, and then we can find an appropriate integer for both sequences and then take the maximum, so then we can take a common integer. So that we have both dxnx is less than epsilon on 2 and dynx, dxny is less than epsilon on 2 for all n greater than or equal to n. So what's going on here? Well, I've got x, I've got y, that's epsilon, and I've just arranged for my sequence to sort of be getting so close to y that it's within half that distance, and so close to x that it's within half that distance, right? So they can't be accumulating in here and simultaneously over there if those are disjoint open sets. So that's clearly going to show that x equals y, but the mechanism for that argument is the triangle inequality, because dxy, by the triangle inequality, is less than or equal to dxxn plus dxny. And, well, it's symmetric, so that is less than epsilon on 2 plus epsilon on 2, which is epsilon. I said I wasn't going to do proof by contradiction, didn't I? Oh dear. Okay, I'll rescue it. It's not a proof by contradiction. I mean, I could make it a proof by contradiction. Okay, given epsilon greater than 0, we can do this, right? Then blah. So what have I shown? I've shown dxy is some real number which is less than epsilon for every epsilon. Well, yeah, don't say it's a proof by contradiction still, because I need to take epsilon equal to dxy. Okay. So dxy must be 0, right? Okay? Right, because dxy can't be less than every positive real number and not be 0. And therefore, by the axioms of a metric space, x must be equal to y. So we're done. All right. Okay, so let's now give a characterization of continuity using limits. Wow. So that comes here because maybe the most important property of compact sets, I haven't defined compact yet, but so let me phrase it this way in order to explain why this is occurring in this point of the course. If I take a continuous map between topological spaces, the pre-image of any open set is open, right? That's the definition. That means the pre-image of any closed set is closed, if you think about it, because you just look at the complements. Now, we've discussed that the image of any open set is not necessarily open, and similarly, the image of any closed set is not necessarily closed. But compact sets, which are a very special kind of closed set, do have this property. You take the image under a continuous map of a compact set, it's compact. So that's a very special property of compact sets among closed sets. And the way we're going to prove that is using, at least in the metric situation, the following way of thinking about continuity in terms of preserving sequences. Okay, so let me take two metric spaces and then a function between them, or between the underlying sets, rather. It's continuous if and only if for every convergent sequence xn in X, we have that taking the limit in X and then applying f to it is the same as applying f to the sequence and then taking the limit. All right. Okay, so suppose f is continuous. And that the sequence xn converges to x. Okay, so we need to show that f of xn converges to f of x. To show that, we need to show, given an epsilon, that we can find an integer such that ... right? So given an epsilon greater than 0, well, and that's all we're given. Now we've got to figure out how to produce an n. But if I've got an epsilon and I've got a point in y, that is f of x, we know that B epsilon f of x is open. So by continuity, the inverse image is open. And hence there exists a delta such that, well, x is in that open set, and by definition of the topology, there must be a delta such that B delta x is contained in that. Okay, so that's just what, ran on in your head as soon as you saw an epsilon there, right? But now I've got a delta. Okay, so the delta I can now apply to the definition of convergence of the sequence xn to x. So since xn converges to x, there exists an n such that for all n greater than or equal to n, xn is in B delta x. Well, B delta x is contained in the preimage of B epsilon f of x. So that means this. And so f of xn will be in B epsilon f of x. Well, that's what I needed, right? I produced an integer such that all for n greater than or equal to that integer, the elements of the sequence past that point were in the open ball that I was given. Okay, so that's it. So that proves that given a convergent sequence, the image of the sequence converges to the image of the limit. So let's do the converse. So suppose that I have that property, and let's prove that the function is continuous. Okay, so suppose f satisfies that condition with respect to any convergent sequence in X. Well, remember we had this characterization of continuity. One was the preimage of any open set is open. The other one was the one that referred specifically to the open balls, right? Which said that for all y in y and for all epsilon greater than 0, for all x in x and for all epsilon greater than 0, there exists a delta such that y, let's stick with a y. Okay, that wasn't literally the same thing as continuity, but we proved it was the same. All right, that's the metric definition of continuity. Okay, so we have to argue that this, so we know this. So to prove f is continuous, I just need to argue for that. Okay, so that is we're given an x and we're given an epsilon. Yeah, I'm going to do it by contradiction, I'm sorry. It's just easier. All right, so suppose f is not continuous. All right, that is the right-hand side, the negation of that is true. Right? So there exists an x in x and an epsilon greater than 0 such that for all delta greater than, I mean, that's the reason I wrote the predicate, right? So you can go through that in your head and switch all the quantifiers and negate the implication. So suppose it's not, that formula is not true, then there exists an x and an epsilon such that for all delta, there's some y which satisfies the hypothesis but not the conclusion. Right, so that's the negation. Which is to say that b delta x is not contained in the preimage of b epsilon f of x. It's the same thing as saying there's some y such that. Okay, well, it's true for all deltas. So what I'm going to do is take a series of decreasing deltas. Doesn't really matter. I can take 1 on n or 2 to the minus n. So let's call it yn, which is in here, but not in there. So that is, it's within a distance 2 to the minus n of x, but it is not, when I take its image, within a distance epsilon of f of x. Okay, so that's the set minus, right? So that's all the things in here intersect the complement of that. Well, what I've done is construct a convergent sequence, right? That's the point. Yeah. Okay, well, then by construction, yn converges to x, and so by the hypothesis, f of yn has to converge to f of x. Well, I can now take that epsilon that I started with, which I was assuming existed together with that x, and I can plug it into the definition of convergence, right? So in particular, there exists, I haven't used n, an n such that for all n greater than or equal to n, f of yn must be within a distance epsilon of f of x. That's what it means for f of yn to converge to f of x. Well, it means for all epsilon I can find such an n, and I can apply that to this particular epsilon. But that's the desired contradiction, right? Because by construction, yn was not in the preimage of this, and I've just shown that at least if I take n large enough, yn is in the preimage of that. Because by construction, yn is not in the preimage of this. And that's a contradiction. Okay, so that contradiction completes the proof. Okay, so definition. A metric space XD is called sequentially compact. If it satisfies this condition that we use to characterize closed and bounded subsets of the real line with regards to sequences and convergent subsequences. So if every sequence in X contains a convergent subsequence, if I just give you a metric space and a subset, so I'm going to abbreviate this to S compact. So a subset is called sequentially compact. So the way I'm going to use it, sequentially compact is an adjective that applies to metric spaces, not to sets, right? So if I have a subset, I determine whether or not it's sequentially compact by asking whether that metric space is sequentially compact, where I use the induced metric. So if and only if the metric space Y, and I take the distance on X restricted to Y cross Y, is sequentially compact. Okay, so applied to the metric space, which is R with the usual metric, this is precisely the thing that occurred in Bolzano-Weierstrass, so we know in particular that things are sequentially compact, subsets of R are sequentially compact if and only if they're closed and bounded. In particular, intervals are sequentially compact. So let X be a metric space. Suppose it's sequentially compact and that I have a continuous map out of X. Well, okay. Let's just do R for the moment, right? So R with the usual metric, and I have a continuous map to R. And I know what it means to say a subset of R is bounded. I just reminded you of that. And I claim the image of a compact metric space is, under a continuous map, is bounded. I'm sorry. I might as well just do the general thing as I plan to. So. Take an arbitrary continuous map, then the image of a compact metric space is itself sequentially compact. The proof is easy, given this, right? So to prove this is sequentially compact, what do we got to do? We've got to take a sequence. So take a sequence, say yn in f of x. We need to prove it has a convergent subsequence. Well, every yn is the image of something. Let's choose something. So say xn. But this sequence of xn's has a convergent subsequence because x is compact. Let's say xni. All right? That's the convergent subsequence. But since f is continuous, when I apply f to it, I must have that x, as I increase the i's, f of xni converges to, well, f of x. So we just need to show that f of x, well, I mean, that's it. I was going to say is in the image of f. But, I mean, that's it, right? So that's a subsequence. That's yni. It's a subsequence which converges to a point in the image. So that shows you that f of x with the restricted metric is sequentially compact. Okay, so applying that with y equal to r with the standard metric, we'll easily recover the extreme value theorem, and that's the sense in which compactness is responsible for that theorem. But we'll do that next time.